Hello students, today we will discuss about small oscillations. So in this session, we will discuss about the nature of one-dimensional oscillator and what is the relevance of small oscillations. And we'll look at which are the different kinds of equilibrium. So oscillations are the symbol system to apply the Lagrangian formulation. So what you can see, an oscillation of a spring on giving a compression or an expansion will produce a bound motion. It will be moving up and down. So corresponding to that, you'll get an amplitude variation like this. Okay, so it found widespread application in acoustics, molecular spectra, vibrations of mechanisms and coupled electrical circuits. So what is the relevance of small oscillations? So small oscillations in general, if you check, all the oscillators are not simple harmonic. So what do you mean by simple harmonic? Those are the motions which undergo oscillatory nature depending upon the force. So whatever be the applied force, in the earlier slide you can see whatever be the applied force, the direction of the displacement will be in the direction of the force. Okay, so if you consider in nature, not all the oscillators are executing simple harmonic motion. So, but if you consider oscillations in a smaller displacement or smaller amplitude, we can see that all the general oscillations of a coupled oscillator can be considered as superposition of independent simple harmonic motion vibrating simultaneously, and those modes are called normal modes. Okay, so any kind of coupled oscillator can be thought of as consisting of independent oscillators vibrating in simple harmonic motion only if the oscillations involve small amplitude, and those modes are called normal modes. Okay, so Lagrangian formulation of a one-dimensional harmonic oscillator can be applied to a coupled oscillator if the small amplitudes are involved. So now let us see what are the specialties features of a one-dimensional oscillator. So for a conservative system, that is where energy is conserved, you can see the potential energy will be always a function of position. It depends only on position. So we can represent it as V as a function of Q. So if there are n generalized coordinate, we can represent V in terms of Q1, Q2, Q3 up to Qn coordinates, which are the n independent generalized coordinates needed to represent a system. So we can obtain, if you know the potential energy, we can obtain the force. The force is given by negative gradient of voltage, potential energy with respect to the generalized coordinate. So in order to for a system to be in equilibrium, the force acting, any force acting on that system must be zero. Okay, so whenever no force is acting on a system, the system will be in equilibrium, which means Gk is equal to 0. G represents the generalized force, which implies you know Gk is given by negative gradient of potential. So which implies the potential, the variation of potential with respect to the coordinate must be 0. So which implies if the first order of a function is 0, which implies it has a extremum at equilibrium configuration. So it could be a maxima or minima. So whenever a function has its first order equal to 0, it implies that function would correspond to a extremum position, which means it could be a point of maximum or a point of minimum. So these are the different types of equilibrium involved. So you can see if you have a potential well like this, if you give a body a motion like this, so what will happen? It will undergo a bound motion. So while in the case of equilibrium, a neutral equilibrium, you can see when you displace this body, it will be moving to the new position. And if you consider an unstable equilibrium, if the ball is on the maximum position, what will happen if you give a small displacement? Yeah, depending upon the direction of the force applied, it may move this side or it may move to the left side. And you can see it cannot climb on its own. While in the case of minimum equilibrium, if you displace a ball to the left or to the right, it will undergo a bound motion. So based on this, you can see that if a system is in equilibrium with zero initial velocity, then it will remain at equilibrium indefinitely. Only if we apply a force or a displacement, it will undergo a bound motion or unbound motion or just a displacement. So there are three types of equilibrium. So that is stable equilibrium. What is the explanation for a stable equilibrium? Which means a small displacement of the system from the stable equilibrium results in a small bound motion, a periodic motion. So such kind of equilibrium is called stable equilibrium. So for example is, if you consider a pendulum at rest position, if you displace the bob by a small amount, you can see it will undergo a bound motion, isn't it? If the bob is released from a height, it will undergo a bound motion. Okay, so that is an example for stable equilibrium. So stable equilibrium occurs whenever the object is at minima. The equilibrium should correspond to a minima. Okay, and while the unstable equilibrium corresponds to the equilibrium where it corresponds to maxima. Okay, so it will undergo an unbound motion in that case. So example is egg standing on one end. So if you keep an egg over here and if you give a force, it will roll, isn't it? Roll onto a new position. Will that come back? No. If it is a flat surface, it won't come back to the initial position. So such kind of motion is called unbound motion. And the other last kind of equilibrium is neutral equilibrium. So neutral equilibrium just means if the system is displaced by a small amount, it will continue to be in that position alone. It won't move about. Okay, so no other position. It has no tendency to move about or away from the equilibrium. So such kind of equilibrium is called neutral equilibrium. So if you displace a coin from one position to another, that would be the new equilibrium. It won't move to the left or to the right. So such kind of equilibrium is called neutral equilibrium. So now let us compare a stable equilibrium and an unstable equilibrium. So these represent the potential versus coordinate, and the first figure corresponds to this need not be the same thing. It just means that there is a minimum. So it corresponds to what kind of equilibrium? Yes, it corresponds to a stable equilibrium. While this also, it doesn't mean that it has to be an equally displaced or potential one. Just means you have a maxima here. Okay, the point of B corresponds to a maximum and this point A corresponds to a minimum. So two kind of equilibrium. So this kind of notation, dependence of potential on generous coordinate, is for a unstable equilibrium. So what is the peculiarity? You can say V0 is the minimum potential for the first case and the corresponding position is given by Q0. And if you try to displace a body here over to a position Q, sorry, or a position P with an energy E, you can see a difference E minus V, total energy minus potential energy will give you a kinetic energy. So the body will be in kinetic energy. Okay, and as soon as it return back to the rest position, it will convert into a potential energy. So that is how switching over between potential energy and kinetic energy will happen. So that is the representation of a stable equilibrium. So if the system is displaced from the point A to the point Q by giving an energy E minus V, and left to itself, the system will try to come in the position of the minimum potential energy. Consequently, what will happen? The potential energy will change to kinetic energy, and at A, the energy E minus V0 will be purely kinetic. So this would correspond to a kinetic energy, and when the system move towards a position P and position Q, it would be a potential. Okay, so that would correspond to a potential. And in the case of unstable equilibrium, if you displace a body from this point B to any direction, it will move to the newer position. It won't it will continue to move in that direction. Okay, so the system will move either left or right to the position. That means it will move away from the equilibrium position. So that is how we differentiate a stable and unstable equilibrium. Thank you.